1, 2, 3, you have Jerry.
It seems like the Zoom has his own plan for today, so I apologize. Everybody see my screen now?
Right now we see.
Yeah, we see.
Yeah, I didn't understand why it got stuck. It got stuck. I restarted this one, and I think I don't know. Anyway, so at least now we are back to business.
Almost everything is recorded, right?
Yeah, I'm recording. In fact, I just got stuck in the middle. I'm glad you said it, because after it gets stuck, it stopped recording. So we start. No, it's recording. That's fine. That's good, yeah. The recording is really important. I think it's very important for you. You know, okay. So I'm opening. It doesn't like me. Let me see here. Good. Now I'm getting in.
Who's the music?
Yeah. Okay. I'm logging in. Well, I forgot what my password is. Anybody remember? I think it's student, isn't it? Student. And I want it to be SQL one page. Yeah. Okay. I don't know why it's asking me for password. I'm going to here and I'm going to the data. I'm getting the data and it should work. It is working. Basically what it does is really pulling the data from, is putting the data. I have that one too here. So maybe I will even do it here. And what it does is really pulling the data from this structure, which is really one long array. And I think I might have it here. No, I didn't put it here. No, I didn't. In a second, it should really open. Yeah, here we go. How does really the data set looks like? It's basically a long row. See, for one picture, you have one long array. It's one long, each row, it's a huge row. You can see there are 784, 783 plus the 0, 784 columns. So each picture is one long row. But how do you turn it to a number? And I did a nice exercise here to express it. I took one of the numbers and turn it. Let me make the screen smaller. The other way I want. This is a nice demonstration. Let's see who would be able to spot it. Say I took one row, I think the fifth one, and it's a number. Let's see who can guess what the number is. This is, I took the row and I took the first 28 numbers. It's the first row here. Then I took the second 28 and put them as the second row. And took the other 28 and I split it to 784. It becomes to be to 28 by 28. Okay, so that's basically one row in here. So if I take number, I think this is it, this one. Okay, if you take all the numbers here and you break it to 28 pieces and you put them as one row at a time, one under the other one, you get this one. But what do we see here? Anybody can a clue which number it is? Can you tell? Anybody?
Which number what is?
Which number it is? It's hard. I know I can tell. See, on the side you have zeros. That's the white. All the zeros are white. Wherever you have 255, it's black. This is like a dot, black dot. So if it's less than 255, it is gray. How gray and how closer it's to dark It's really how close it is to 255. The closer it's to 0, it's too closer to the white. The closer it's to 255, it means in this cell, this is really a dark. So if you look at this one, you look at the number here, this is basically the same thing as here. If you look at this area, you have numbers. Do you notice there are numbers here? All those one are the darker. Here, zeros means this is really the white inside the number 5. You see that? Everybody got
Yeah, I
it?
see that. That makes sense. That's the
Here.
pixels inside? Is that the
Exactly.
pixels?
This one is the pixel.
Okay.
You got it. You got it. So the top left is white because it's 0. It is 0 here, it's white. This is beautiful. You know, first time I think you understand that an image, it's really a bunch of numbers.
Yeah.
And the beauty here, every pixel carries a number. And if I look at black and white, the numbers move from 0 to 255. That means how gray it is. So here, this point, it's gray. You see that? This is gray. This is probably the 79 right here. See that?
Yeah.
Not exactly white. It's not dark. It's closer to white. So this is quite grayish when you're closer to the white. Okay? So you can see. And then on the top, there are all those zeros here. That means this is the area here, which is white. That's pretty cool. By the way, if I were to ask you, how do you make how do you make a colored picture? That's pretty cool. You will have 3 matrices like that.
RGB, right? Like that?
Exactly, you got it. And each one of them is from 0 to 255. So how dense it's each element of the color, together every cell has 3 numbers. You combine 3 colors, and that's you get a colored picture. That's pretty cool. So really, now when you think about a video, what is a video? A video, it's a collection of pictures. That's really what a video is. So think about it. If I record, when I'm recording matrices. You know, about 18 to 20, that's about the right speed for modern movies. And 19 pictures, let's say, every second, that's a movie. So you can multiply, you can know how many matrices you have. Now, when you have a matrix, you can take the matrix, instead of keeping it as a matrix like that, you can convert it to a row. That's what they have done here. And you can go back and forth, you know, from this structure to this structure. And if you follow the code, you'll see the code how I did it, moving from here to here. But I don't really require, but this is really cool. First time you can see, really, I see number 5 here. So this is really why I have the dark numbers. That's the meaning of the data. And that I wanted to describe in the essay, okay? In your paper. I want to go back here, okay? So this is really the structure of every row. By the way, in the target, it tells you that the first row, what number it is in here. So when you look here, when I type image number 5, this number, I took it from the other array. So if it was the 5th, something here, I took the 5th one here. It happened to be 5, yeah? And the 5 represented by the 5th row here, okay? So the 5th row, coordinate was the 5th location here. This is really 4 in Python, but let's ignore that for a second. I took this, that tell me what the number is represented by this long array. And this long array, as I showed before, you can really present as in this way. Every row, it's really a number. That's pretty cool. So that's the data. We put the data from package in Python, and that data is long array for each number. And by the way, you have 70,000 rows, meaning I have 70,000 numbers. Some 3, some 8, some 4, okay? And all of them are handwritten numbers. That's describing the data. So here is more examples. This is a little more condensed. And if you want to see how those numbers came from the code, just really putting some specific record, I know that they are representing those numbers, different numbers. Just another several rows representing zeros. So this one, if I want to describe it here, it probably will have, you know, around will have numbers that are not zero, and around inside and around will be all zeros. And wherever is dark will have a 255 or closer to 255. So if I look at this one, really all those places would be 255 in the pictures. So that's describing the data. That's point number one in the assignment. Every questions? That's a good time. Okay. So by the way, remember in the other chapters, chapter 2, we use the data, we download it from the internet, and it was compressed. Here I just showed you that I built that special object, and you inherit from it, and usually that's what we call the constructor, and that really does usually the work, okay? I don't really require you in the exam. I most likely will not ask that way. I don't really, that will be too much. But if you really want to follow for the future, here you have the code. By the way, for chapter 3, this is the object, okay? And the object is inheriting. If you follow, it's inheriting from the basic objects I created. And this one is sitting in the utilities. This one does a lot of work. So I don't have to repeat it every chapter, like saving an image. I don't really, you know, honestly, I forgot how I did it. And I don't care anymore. I just know I have a function. I want to save an image. I plot it. I say save it. And he knows automatically to put it in the right chapter, blah, blah, blah. That's a beautiful structure. So this is the object for chapter 3, inheriting from the basic object. And since it's inheriting from the basic object, you also have a save function. It has a lot of other functions, okay? That stuff I do require, that you know at least the basic. Okay, so get the data in this chapter is different than chapter 2 and different in chapter 1, if you follow up, okay? Let's move on to the next requirement. Discover and visualize the data to get insight. What do I mean by that? Let me show you. Let's look at the chapter itself. You know, this is really visualizations of the data, okay? Now I saw the data. I really understand how the structure of those images, how the belt, okay? Could be there any problems? Can I do something about them? I don't know. One thing I might do, okay, which I even haven't done here, you can propose suggestions, okay, is to make sure that I have, you know, or take into account how many zeros I have or ones. But that's what we'll get that to later on. But basically, this is visualization of the images. We took every row, we took some rows, sorry, not every row. We took some rows, different numbers, and those rows, we painted them here. How do we paint them? We simply convert them to this structure, every row that we wanted to print. And there is a function in Python that takes this image and turns it to an image like that. Basically, turning according to the intensity, the number, it's the intensity of black, and that's the way he's painting. So that's the visualization of our database. That's a good description of what we did here. Questions so far? So we already kind of covered 2 points. Yeah, 3 in fact. That's the look at the big picture. We'll come back to that. I'll cover that again in the end. Okay, after we, I don't know why I have this caption. No, this should be something else. Okay, let's go on. That's the description. Let's go on. Let's see what else we did in the chapter. Then we said, okay, we need now an algorithm that will forecast or will be able to forecast if the number is 5 or not. By the way, you will ask, why, Amos, did you do that? And why in this chapter, the question was posted that way. This was really a step on the way. The real answer should be, the real challenge in this assignment, when I get those rows, when I get that row, which represent the picture, can I, from this row, project what or predict what's supposed to be the real number? For example, when I look at this row, this is a row, yeah? Can I say this is a 5? Can I teach an algorithm, give him this data, give him a lot of this data, and then give him a new one and ask him, what do you think it is? Can you do that work? One more time. The objective of this chapter, it is to see if we can find a classifier that can, based on the row of the data, it will convert it, he will do whatever he wants, he can convert it, and then he learn that this one's supposed to be 5. So he should have the mechanism to connect between this kind of numbers to the number 5. And I give him a lot of them. There are 70,000. We'll split it to 2 in a minute. But I give him 60,000. Learn from me. After you learn, show me that you can really do a good job in predicting numbers. When I give you something like that, can you predict which number it is? So basically, I would like him to be able to predict all the numbers 0 to 9, all the digits. For now, I'm making a simple objective. Can you predict if the number is 5 or not 5? That's a different question. Fair enough? Everybody got that point?
What's so far?
One more time. We're breaking the challenge to 2 parts. Part number 1 is I show the algorithm all those rows. I tell him study it.
Yeah.
He learn it. How does he do it? It's a more advanced course. We won't get into it. Okay? But I mentioned some algorithm like, you know, the stochastic descendant gradient, and we'll talk about random forest. They have this ability. They learn, and then later on I will show him another number, another row. He has the ability to predict. Now I want to see how good does it do the job. So stage number 1, instead of asking him, you know, which number is every row, I'm asking him, is it a number 5 or it is not a number 5? That's much easier question. Is that right?
Hello?
Yeah, do you got it? You know, I'm showing him 60,000 rows. I tell him study it based on the result. He studied it. Okay? Then I tell him, you know what? I give you a new row. Can you tell me, is it a number 5 or it is not? I didn't ask him which number it is because it could be 4, 3, 2. Or would I ask him, is it a number 5 or not a number 5? You got it? That's much easier question to the algorithm. What is my data set? My data set has 2 parts. This is what the pictures look like. And this is, I know what this is supposed to be. So I have a lot of rows representing all the numbers. Now, this array show me 0 up to 9. But really what I want him to learn, it's not which number it's specifically. I want him to learn, is it a 5 or not a 5? So we took the challenge. So if I want to answer the question in, you know, in 1, what is the objective of this chapter? It's really to find out which algorithm can predict every digit, but we're doing it in 2 steps. First, we learn how algorithm can distinguish between a specific number to the rest of them. Is it that number or not? And stage number 2, we extend it to more to say, can you predict which number it is? That's what we'll do at stage number 2. Okay, so we're gonna prepare the data. For stage number 1, how do we prepare the data? First of all, it's very easy because we already have the data. We go back to here. We already have the data. I think I have that one here. We already have the data organized nicely here. We need one row that I don't show here, but we really need to take, we need to take this long row that has 0 up to 9, and every number that it's not 5, turn it to 0, and every number that it's 5, leave it as 5. What does it do? It really means that I have only 2 types, 5 or not 5. Later on, we made it more elegant, saying if it is a 5, turn it to a true. If it is not 5, it's false. So we're turning all these numbers, instead of saying 0, it will say false, false, false. You will get to number 5, it will say true. When you get to number 9, it will say false because it's not 5. That's what we do here, by the way. That's the next, preparing the data. So here we go. If you see this code, it's saying if y train is 5, what it really does, this one return true. So I'm making a new variable called y train 5. Is holding, if it is 5, it will put true. If it is not 5, it will put false. That's very easy. We do it also for the test data. As I said before, stage number 1, what we're doing here, the code does, takes the whole 70,000 rows. I have 70,000 rows here. I split them to 2. 60,000, we're going to use them as a training data, and 10,000, we're going to use them as a test data. So far, so good?
Yeah.
Beautiful. We have to make sure, of course, that we're pulling the data, you know, the 60,000 and the 10,000, we make sure we have all the numbers in the 60,000 as well in the 10,000. Not just take the 10,000 to be all 9 and the other 60 would be all the other numbers. So I can't really study about the 9. That would be wrong. So I have to shuffle the data to make sure I will have all the numbers in the training data set and I have all the numbers in the test data. That's a very important in describing the data and how we prepare in preparing the data. So beautiful. So we prepare the data by having training data sets with its target, the label. We have the test data with its labels. We mix them up and we make sure we convert both of them to binary. Binary means, so if it's 5, it will say true. If it is not 5, it will say false. That's a binary variable. Has only 2 possibilities, true or false, 0 or 1. It's equivalent. So far, so good. So we are done with preparing the data for this chapter. That's what we did so far. What the next stage we have, so here, and refer also to chapter 2, okay? Now we have selecting a model. Which models that we use to train this algorithm? So if we go and we see, we used algorithm called SGD, by the way, it's stochastic gradient descendant. It's a beautiful algorithm. I wish we had the time and to really show you what does it mean for the mathematical point of view, how does it do it. But for this course, we don't really need to. The only thing is, it's already an object that Python have prepared for us. Whoever wrote this scikit-learn library, he made a sub-library called linear, and this is one of them. It has several of them there. So we're going to use this one. So we're creating the object, and then we use the fit. Remember, every object in scikit-learn has 2 functions, basic functions. It has more than 2, but 2 important ones. One is fit, one is transform. And the transform, it's applying. What it does in the fit is learning. So it is learning from the 60,000 rows and the 60,000 labels. Now we learn, so it's kind of keeping it to himself. So SGD, CLF, it's really an object that know already the relationship between a long row to what number does it represent. That's, we train the algorithm. That's what we do. We train the algorithm. Okay, then I have a predict, you see, okay, I did the fit, okay, and now can I predict? So I give him a specific digit. By the way, if you look at the code on the top, it's really the sum digit. It's nothing but one of those rows. It's row 36,000. It's happened to be that I know it's a 5. And this one is just taking it, converting it to 28 by 28. Exactly what I did and show it to you. And then this is really what this image is. It's a NumPy array of 28 by 28. Okay, so I'm taking this one And I'm telling him, please predict it. What is it? So I gave it to him as input, and he gives me an output, and he said, yeah, it's true. Because it is really, in fact, he's predicting correctly that it is 5. That's really what he did. Okay, but just doing it on one case, that's not a serious one. I want to see if this stochastic gradient descendant, which I don't really know how it bet, you don't know really, for your point of view, you don't really care. You just want to know if he's doing a good job. That's the next part. It's called performance measurement. Is this algorithm does a good job? Okay, and how do I do it? I say, you know what? I have 60,000 rows, is that right? I split it to 60,000. And what I'm going to do now, this is really beautiful. Let me even use Excel just for demonstration. Think about it, you have a row that has a lot of numbers. In the beginning, they're all zeros. You know, when you don't have any gray area in the picture, and then you start getting, you know, 255, blah, blah, blah. And you have a lot of columns. I'm not going to do all the columns. I just put 3 dots. That means it's a long column up to 784 columns. Okay, and then here it says 5, which that means this is, I will call this one, let's put an insert. This is really my matrix X. All of that, that's the matrix X. All the rows, each row represents a number. This is my Y. This is my Y trend 5. And this says, it doesn't say 5, it says true. If it is 5, if all those ones represent the 5, that will be a true. If another number, you know, I have a lot of sequences here. Okay, I'm just making it up, etc. You know, you have all those numbers representing another number, okay? And that's, let's say it's 6, so it will say false. I have 60,000 of those. I have 60,000 rows like that. And I tell him, study for me. You know, somebody had a good idea. I said, you know what? Let's do it in a different way. To go and train this algorithm by splitting those 60,000, you know, instead of 60, I will make 60,000, I'll make 60, just for illustration purposes. Let's say I have 60 rows. I'll just make some numbers here. You know, it goes up to here. Okay, so instead of 60,000, every one it's a thousands, okay? So I have a lot of zeros, and usually in the beginning of a picture, it's all zeros. So I have 60,000. I take the first 40,000. I take the first 40,000, let's color them. Fair enough. The first 40,000, let's make the first one as well, part of it. And I said to the algorithm, study the relationship between every row here to what it is here. Let's say here I have another true. Let's say that this one is also a 5, okay? And this one, it's a false. You should have a lot of false, yeah? Because, you know, you have only 1/10 of the numbers are true, you know? Fair enough? Okay, so he's learning from those 40,000, and then I have another 20,000, and I'm telling him, you know what? Let's see how good now you do on those 20,000. In another word, I'm putting, let's make a different color. Okay, I have a lot of other numbers here, you know, let's make another example. You know, eventually it's supposed to be, you know, let's say the first one, it is false, meaning let's say it's number 7 or whatever. What I'm asking the algorithm, split the data set of the training to what we call cross validation. We covered it in chapter 2. We take 2/3 to train the data, and 1/3, we're asking him Okay, take now this row, tell me what you think. And he is predicting. He said false. If he says false, that means he predicted correctly. Is that right? If the second one is true, meaning it is 5, and he said false, so it means it's not predicting right. Everybody got it? Hello? Hello, guys? Anybody home?
Yeah. What was the question?
I'm saying everybody got the idea. I'm splitting the whole training data set to 3 pieces. 2 pieces for training, 1 piece to test. So I'm telling the algorithm, study whatever the relationship is between every row to whatever the result. Then I want to see how can you predict. I know the real, what that represents. I know the first one it's a 4, that's not a 5. The second one is 5. And I want to know if the algorithm can predict. So I'm giving him this data for prediction, and he is putting his results here. Here, let's say it says true. That's his prediction for every row. So I want to measure how accurate is this algorithm. What can I do? I can see how many he got right. Am I right? That's good accuracy measure.
Yeah.
You got 90% correct. He's probably doing a good job. Is that right?
Yeah, but that's if he has the answers beforehand. If he doesn't, then what do you do? How do you know if it's accurate?
No, I know the answers. That's why I'm keeping those ones. I'm keeping another third of the data, and then I can measure his prediction. I'm giving him only those ones. He's not using those ones. He never saw those data. So this is one round. I can tell him now, let's change the game. You know, I will give you the first third. Use this first third. Let's change. You know what? Let's change. Sorry. I give you only the first third, but I want to give you this one. I give you the second third. I'm not giving you this one. Okay? But I will give you the first and the third. So here's all the data in yellow. Now I tell him, you know what? Go ahead now, study from the first and the third, and then after you learn the relationship, predict what do you think about those ones. And I would check his accuracy. I will do the same things. I'll give him then a third time, I'll give him only the other 2/3 and ask him, can you predict this one? That's called cross-validation method. We talked about it in the second, in the chapter 2. I just wanted to review that again here. So now that we have, in fact, I have all his prediction about all the data. Every time when I'm trying to see if he's predicting, I'm not giving him this data to learn from. So now I can check his accuracy level, and his accuracy level could be a good predictions, good performance measure, how well that algorithm does. The higher his prediction rate, the better it is. That's what I would think, and in a minute we will expose the discussion more. So that's what we do first. We give him, by the way, Python has a very nice algorithm that can really do all the work. Here we go. This function cross-validation, if you, let me increase the font, you can see it better. It does all that work that I just talked about in one command. Cross-validation, I tell him, do it for this algorithm. I give him CV, it's cross-validation 3/3, like meaning split the data to 3 and do this process that I just told you. And then I want you to tell me what the accuracy of that algorithm. And his accuracy for the first third was 95%. Second third was 96%. For the third third, it had 96. So in another word, when he was predicting the first, you know, when he studied from the other 2 and tried to predict this one, he did a good job. it predicted 95%. That's the beautiful about this command is immediately does all that hard work and immediately tells me the accuracy of that algorithm. That means it's doing not a bad job on the training data sets. Is that right? 95, 96 is pretty good. Although today there are a lot of algorithms that can get you to over 98%. Okay, they are more sophisticated like, you know, like a neural network or convolution neural network. They are really sophisticated. It's really required a high math level, like a PhD level. So I won't go into that. I don't even go into that stochastic descendant gradient or stochastic gradient descendant. But at least you know what that algorithm does is has the ability to learn, has the ability to predict, and now Python have given us a function in this library scikit-learn that can even measure how accurate it is. Okay, that's pretty good. Okay, by the way, to make a point, 95, 96 makes it says that is a good predictions. What do you think, guys? Is it a good or is it bad?
95 is good.
That's good. Okay, let me tell you, I'm Amos. I am an algorithm. And I can predict 90% right. Would you say it's a good or bad?
Well, before you said 90% is good, so I'm going to go off of that.
Okay, but see, I'm going to trick you now. What is my prediction supposed to be? Is it 5 or not 5? Is that right?
Yeah.
90% of the data, it is not 5. So you know what my prediction will be always? It is not 5. If I am an algorithm, stupid algorithm, I would call it, although I think they called it here naive or never 5 classifier. It's like, it really is a way how you build your own classifier. Okay, but this is, I call it a stupid classifier. Why? It says, you know, I always going to predict it is not 5. How many times I'm going to be right? 90% of the time. Because 90% of the data are not 5. Everybody got it?
Yeah.
You know, it's really funny. You would think if I'm right 90% of the time, I must be a good classifier. But in this example, it really depends on how you phrase the question and what is the structure of the data. The way I phrase the question is, can I predict if it is 5 or not 5? And I'm very good on predicting not 5 because 90% of the data is not 5. So I will tell you it's not 5 all the time. So I will be wrong 10% because 5% of the data is 5. That's what will be my error, but I will be right 90%. That's a stupid algorithm. And we have to find a mechanism to take care of it. So, you know, even a stupid algorithm can give 90%. Now you will say, maybe 95 is not that good. In a minute, we'll reverse that and we'll have a measure that will be better than just accuracy. So accuracy is not always a good measure in how good is an algorithm does. And that's your job in picking up a model. You want to pick up a model that have a good performance measure, but accuracy, apparently, it's not a good measure. And that's why please do write it in your own word in your assignment. Okay, what is a confusion matrix? That's come to help us to measure how good is this algorithm. And here, you know, all the, you know, the cross validation, you run all of that. What you need for cross validation? Let's go back to the Excel. After we do that cross validation, we can think about this huge giant. We have 2 columns. Is that right? I'm just trying to make it up so it will look like similar to what really in reality. Okay, let's put some false, true, false, and that should be more false than true. So I'll just drag it and I'll just make it like real life kind of. I'm just, you know, never mind. Let's write here false. True. Everybody got the idea what I'm trying to do?
Yeah.
This is the real, is that right? That's it, this is the real. Let me copy more false. And you know, on the right side, that's what the algorithm have predicted. I'll just copy it for convenience. It's definitely not going to be the real one. Let me just copy all of those. So it have like kind of look like, okay? And let me copy those ones all along to the whole column. So this is the predicted. I'm just making it up, of course. Now think about it, that you have those two columns, the true one and the false one. There are 4 possibilities. Every time in reality, let's call the left side the reality, real. And that one we'll call predict. Now, we will have 4 possibilities. When in the real time it is true, I might be right, and I also predicted it to be true. That will be this. So I can count, let's call it the number. When it's true, I predict it also true. Fair enough? That could be many cases. Which cases will be? Let's take one example. Let's say true. Let's change that to true just to. Okay, that will be a good case. This is one. When it was really true, that is 5, I also predicted 5, so I was right. So I can count all those combination of true, and write that number right in here. So let's say I have 200, I'm just making it up, you know. Let's say 45,000. We have 60,000 cases. 45, it was true, and I counted that true. The other one could be in the real life, it was not 5. But this is really should be a lower number. That should be about 10,000. So let's be closer to reality. Let's just make it, even make it more fun. Let's make it 9. It probably should be around 7,000. I'm just making those numbers closer to reality. This one should be around 45,000. Okay, because we have more non 5. So this is like a case on which I know it is not 5 in real life, and my algorithm predicted false. This is another case. This is another case. So I'm counting all those cases in which the left and the right will say false. Those are the numbers I'm writing here. What are those ones? Let me just move this one. Let me just write here, true, false. That will be better, I think. Will make more sense. And I will write here, true, and I will write here false. Fair enough? So, 7,500, I was absolutely right. This is good. The higher the number here, the better it is. Something is here. The higher the number is here, and I would like not to have any number here. A good algorithm will have a 0 here, a 0 here. Is that right? Because this is max. In real life, it's true, but you made a mistake. You thought it's not a 5, but it is a 5. Let's find an example. True, false. Here we go. This is 1. In real life, it's true, but you predicted the false. You made a mistake. So let's assume we had about 4,000 of those here. Okay, so this one should be really, I think, 2,500 if I'm not wrong, will give me the total 60,000. So those are wrong, and those are right. Those two. This is really, the higher those, the sum of those two, the better is the algorithm. Does that make sense, guys? When it is a 5, I would like him to be able to predict that it is a 5. When it is not a 5, I would like him to predict it's a 5. But if it's a 5 and he says it's not a 5, he made a mistake. When it is not a 5 and he said it is a 5, that's also a mistake. That's what we call a confusion matrix, by the way. That's what is known as a confusion matrix. So if we go back to our text, this is really how you write the code, and you find out that in fact, out of the 60,000, you had 53,277 predicted correctly. It is not a 5, and 4,344 it predicted correctly that it is a 5. He made some mistakes here, okay? When it is not a 5, he said it is a 5. So this is an error, okay? It is in real life. This is in real life not a 5, but he said it is a 5. And here he made another mistake. When it is in real life, it is a 5, he said it is not a 5. So there's two types of mistake that he made. The higher those numbers, the worse is the algorithm. This is what we call a confusion matrix. We use a confusion matrix to build up and measure how good is the algorithm, and we do not want to rely on the accuracy, because accuracy, as we saw before, might not be a good measure. So here we go. We have two measures, one called precision. How many times I predicted true and I was right? One more time, precision is out of the numbers that I said there are 5, how many times I was right. That's precision. So in another word, I said all of those are 5. So this is the total. This is, by the way, this is the number of 5, and there were really 5. This is, I said there are 5, but there are not 5, because I said there are 5 and there are not 5. So that will be the error. So here, by the way, this is precision. Out of the positive, or the one that there are not 5, how many I was right? And this the precision. Recall, on the other hand, out of the one that are actually 5, how many I was right? And here is a little picture describing those relationships. If I have here the predicted, here is the actual, the way I pictured that before. All those I was right. All of them are not 5. Therefore, I was right here. Depend on, my definition. So some people, I usually call those one true positive, but it's really semantic. If I define non-5 to be negative, then it means true negative. I was right. I kind of converted the sign of each one of them, but let's stick to this picture. The actual, the numbers are, I have some numbers that are not 5, and I was right. I said they are not 5. So I have 1, 2, 3, 4, 5. Occasion, I was absolutely right, saying they are not 5. On the other hand, there are 3 times that the numbers are 5, and I was right on predicting they are 5. So this is good cases, and those are good cases. The higher numbers of cases here and the higher numbers of cases here, the better is the algorithm. On the other hand, what happened here? Here, in reality, it is not a 5, but I was wrongly said it is a 5. That's why it's a false positive. I made a wrong decision about that number. So, in another word, how many times did I say there are 5? 4 times. 1, 2, 3, 4. So if I look at this equation of precision, the denominator will be 4, the numerator will be 3. So it'll be 3/4. One more time, I made 4 decisions that it is a 5. I was right 3 out of the 4. That's what we call precision. Because I had 4 positive. I made a mistake here. So how many out of the 5 that I claimed are 5 I was right? 3/4. Okay, on the other hand, in recall, I was right. This was true positive. Okay, and what is false negative? That means when there are 5, I wrongly classify them as negative. One more time. What is false negative? False negative, when they are 5, I said they are not 5. So I made a call on those 5 cases, okay? They are all 5, and my decision was that only those are 5, but those are not 5. So I was wrong. I was wrong on 2 times out of the 5 times. So what my accuracy on recall, I will take the denominator will be 2 plus 3, the denominator will be 5, and the numerator will be 3. That's called a recall, okay? So I have 2 measures. What do I really would like a algorithm to be? We said we want the algorithm to be such that this will be 0 and this will be 0. If this will be 0 and this will be 0, the recall and the precision will be 100%. It will be perfect. But usually it's not the case. And there's really a trade-off between those two. An algorithm has to make a decision based on some statistical measure, the way finding relationships. And we call that measure internally. You never really see it unless you ask him to pull it out. You pull it out from there. It's a threshold. And that threshold tells him, if I get a grade for someone, if it's above something, I would say it is a 5. If it's below, I would say it is not 5. And depends on the threshold. Usually, and this is really almost the case, almost the case always, the higher is when the algorithm is predicting precision good, is doing less good a job on this one and vice versa. That's what we call a trade-off between precision and recall. So somebody said, you know, don't measure the performance just based on precision. Don't measure it only on recall. You have really to take something that combine those two, and that's come a test called F1. F1, it is a kind of, it's known as a harmonic average. You don't need to remember that. The only things is, just remember that it's really taking the two together. If you notice it, you don't really have to remember the measure. You don't really have, you just have to remember that F1 takes into account the recall and the precision as a measure of performance. Is that the best performance? Depends. Usually it's not a bad one because it combines those two. But you know, there's a lot of very good cases here described in the case. The last time I gave an example on, God forbid, cancer, you know? And I would ask somebody, you know, is that important for you if I write an algorithm that can test if you are sick and that you have a cancer or not? Which kind of an error you will accept? If I will miss diagnosing you that you have a cancer, will you be mad at me? Or you will be mad at me that I tell you you have a cancer, but you really don't have a cancer. And depends on that answer, I can tell if it's more important for him that I will give him a higher precision or I give him a higher recall, okay? Say if he is scared that I always will be right, okay, then he wants really a recall, a very high recall. Then it means that if he has a cancer, I will get it. Then he wants a higher recall. The other way is around for the other case. Play with that a little bit. The first time you hear it, it's very confusing. But the more you play with it, the more you get the idea. So here we go, by the way, in this trade-off, there's a nice explanation, go over it. But the bottom line, really, what I really want you to remember, it is this diagram. You know, every algorithm has its own threshold inside. You don't even know how it works and how we build it. But the higher the threshold, the recall goes down. It's just internal decision. And then the higher is the threshold, the precision. But the key point is if the recall goes down, the precision goes up. You can take this picture and convert it to another picture, which is like that. You can see here, the higher is the recall, the chart shows you that the precision will be lower. So if the precision is very high, the recall will be very low. That's equivalent to this guy. If our precision is high, the recall is low. That's really relevant to this one. And then the other extreme, when the precision is very low, the recall will be very high, and will be this case. So I can make a little chart here, and then everybody can decide where to put the threshold and decide which kind of how the algorithm should make his decision based on this point, and then I will get a recall of that level or precision on that. Some people will say, you know, recall is very important for me. I can't tolerate any misrecall. Because if I have a cancer, I do want to make sure I really know that this algorithm will find it. And then I can take a treatment. So if he makes a mistake, sometimes and tell me you are sick and I'm not sick, well, no big deal. So I did extra test. I can tolerate it, okay? So that's the importance of this chart. This trade-off between recall and precision, extremely important. The chapter talks about how you can create your own algorithm based on this one by choosing different threshold. I won't get into that. What's really important for me that you know to distinguish what is a recall, what is a precision, and there is the trade-off between those two. Now, the closer this line upper, the better it is. That means, you know, you would like, you know, if you choose here, you know, if the curve goes here, and I would choose this point, I would have a high precision and high recall, okay? That's one thing to notice here. But let's move to another very common, most likely if you deal with this and you'll be a manager one day, you most likely, you will see the second measure, it's called ROC, Receiver Operating Characteristic. The idea is very similar to this recall and precision. They just use one other one instead of the precision. They use the recall the same way, just give it a different name. They call it true positive rate, but in reality, that's why I marked it bolded, so you will really realize this is really the recall. So ROC is built on very similar concept. One is the recall. How many cases out of the cases that are positive, I was right. The one that I said they are, out of the one that are positive, how many I detected, they are positive. That's the recall. The other one, it's what is known false positive rate. That means I said it is positive, but it really isn't. So let's go back to our chapter, the pictures, false positive. Let's go here up. And what is it, false positive? This is this one. So I take true positive plus false positive and divide it. So the case here, this one will be, really if I take it, it will be 3/4, 75%. That one we call false negative. And I give it a name. You can really, 1 minus sensitivity, you can read here. And I really do require that you know that. You know, you can read it one time. So the false positive, it's nothing but 1 minus what it calls specificity, which is a true negative. Just play with those one and you get the idea. I want, you know, our time is running out and I want to finish what you need for the assignment. But this one is really based on the same idea. And now we're making a chart, the trade-off between true positive rate, which is the recall, and the false positive rate. And that curve known as ROC, very known chart. The algorithm, every algorithm will generate this kind of curve. Which kind of an algorithm is a good one? The one that this curve will be as close as to the one. If it touches the one, it's a perfect algorithm. And why is it really important? Because I will be very, see, pay attention here. I can give up a little bit of the false positive rate. I get to this point, I'm getting really high, almost 85% or 90% of recall, which is really good. I'm really giving up only 5%. That's excellent. So I have false positive rate, so I'm only 5% telling people they are sick in cancer, but they are not. So those 5% will say, well, I can bear that. Okay, you took me to the hospital taking tests, which I shouldn't, but I rather to be sure that 90% of the time you are right, and this is good, okay? And if the algorithm is higher here, it means I'm really getting you 98%, telling you, sure, you have a cancer, 98% right, and only 1 or 2% that I might be wrong. That's even better. So how do we compare two algorithms? We run the algorithm, the whole process on both of them, and we create the ROC to both of the algorithm. Anybody wants to see the code is right here. And in fact, if you go into here, I made it for you. You can see the code, all the code. I think it is right here. But it will take him a little time to run, so we'll wait for him. When he shows, it will show you basically this picture. And the nice thing is that here we see the random forest is another type of algorithm, very sophisticated, uses a lot of multiple algorithms, you know, many trees, I would say. It's based on decision tree. It's like a forest of trees. And it really, like almost perfect. Pay attention to it. This is beautiful. Now, somebody said, can you summarizing this picture by a number? And we got to a concept called, you know, the accuracy under the curve. It's right here. It's the accuracy under the curve. What is that measure? For the SGD, it is all this curve. If you see all the curve, everything's under the curve. That will be probably here about 90%, I would say, or even more. Okay? Because, you know, if you are totally random, if you are a naive or stupid algorithm, you will be right on this line if you do randomly. If you are a good one, that curve will be higher. The higher, the better. And we can see random forest will be closer to 99. And in fact, the numbers are here. And I think we got, here we go, random forest is 99.3%, which was extremely good. Okay, AUC, we have a function that it knows how to do it automatically. So getting this picture, we have all the tools and all the algorithms to do it. But what I require you to do in the assignment, describe this chart, what is ROC about, and why it's a good measure for distinguishing which for a model selection. We're selecting between SGD and random forest. Based on ROC, we should choose the random forest. It's giving a better result measured by the AUC. I think this is really mostly what I wanted you. There's only one, and I will be forgiving if you don't get it right, but this is a beautiful, and I will close the session for today. You know, so far, we did the first half. No, sorry, there's two more things. One, I do really require you. Up to now, we did everything, distinguishing if the number is 5 or not 5. The second part, by the way, the algorithms, everything's work exactly the same. The only this one is that is really forecasting exactly which number it is. One more time. Really, now, instead of changing the Y, if you recall in the very beginning today, we changed the Y to be, is it a true or false? I will steal 2 more minutes from your time, apologize. Here, we turn the Y training, is it a 5 or not a 5? Now, we're not doing it, we're using this one. This is mean all the numbers. So I need to forecast not only if it's a 5 or not a 5, we're forecasting all the numbers. And there's many ways to do it. I will just mention this most common one, and that's enough for me. It's very rarely we use OVO. Some algorithm needs the OVO, they are more efficient running, but most of the algorithm really use O versus A. What does that mean, all? You know, I can do the exercise. Is a number is a 5 or not a 5? I can run again. Is the number is 4 or not a 4? I can run it again. Is the number is 2 or not a 2? And then I will check all those 10 times, and I will see which one it has the highest confidence or higher threshold, I would say, or confidence of the algorithm to say this is 5 versus the other one. On the other hand, if is it a 2 or not? He said, no, it's not a 2. The other one, he said, I asked him, is it a 3 or not a 3? He said, it's not a 3. On the other hand, on the fifth one, he said, it is a 4. More than it's not a 4. So then I would say, this number is probably 4. I would do it for another number, the same things. This time it comes to be that the second one was right. When I asked him, is it a 2 or not? He said, yeah, it is a 2. So I would say, okay, my algorithm will pick a 2. You can tell that I really need to use like 10 algorithms to work parallel, and that's really the way it works. He ran it 10 times, and based on the one that gives him that it is true, that it will pick that one up, okay? Then from that one, I will skip all that one, and I want just to jump to this one, which is the seventh confusion number. This time, this is all the true numbers, could be 0, 1, 2, 3. So we have 9, 10 rows, and we have a 10 column. Why is that? Because there are 10 type possibility, and my prediction could be one of those 10s. So what does it mean, a big number in the middle here? That means when it was a 0, I correctly said it is a 0. What does it mean when I have a big number here? That means when it was 1, I predicted it's 1, etc. When it was 2, I predict. So most of the time I'm doing a good job if you look at the diagonal. Diagonal, big numbers in the diagonal, it means every number I predicted it correctly. Now, this is hard for the eyes. So what people usually do, they turn these numbers into a picture. So when you see a high white, that means you're doing a really good job. So when it's 1, I really predicted very well that it is a 1. See the number here, not surprising, it's a really big number. 6, 4, it's higher than 4, 7. This is a little grayish. This is wider. So the higher the number, there's a function in Python that can make a picture out of numbers. This is good for the eyes. By the way, I made also that it can make it as a color. So I can make it as a color. And really nicer. And there a bar, the yellowish or the reddish it gets, the better it is. I don't forget the other side, the bluish, I think it's getting, the worse it is. So this is really like will turn to a bluish, and those one, this will be close to yellow, red. That means it's really accurate. I will finish the session today. I will stick 2 more minutes. What are we doing here? Here we basically say, you know, Amos, we don't really have the same number of cases of 2 as we have number 1. So we might not doing a good job here. Why don't we divide every row by how many numbers we have of that digit? So if I have 10,000 zeros, I will divide this row by 10,000. If I have 7,000 of ones, I will divide this one by 7,000. It will change the weight. I will be more accurate. And that's really what we do here. And then later on, we just chop the diagonal because this is we know we are right. We are interested how wrong we are. So what this image shows is, for example, okay, I have a big error. When it's 3, I get confused and I say it is a 5. When it is 5, I get confused and I think it is maybe 3. Sometimes I get confused, it is a 8. Because this is my prediction, this is the real. So here is, when it's a 5, I get confused. I think it is 3. When it's a 5, I also get confused and I say it is length. By the way, when you see a lot of light ones here, that means I tend to make a mistake with all those numbers and tend to say they are 8 when they are not, okay? The places that is white, it's where I make mistake, like we converted here the logic. And that's really concluding what I expect you to describe. This one you can skip. I gave you one question that I required about the multi-level. The question is good enough if you understand it. If not, I will go over that next session, okay? This one a little quick Question, guys? Anybody? Tal?
No, thank you.
No,
Okay, is that
everything-
clear? I think I went a little fast. I will go over it again next week if you want. But what I really want you to do, go over the recording and just put it in writing. And the better you do, the higher will be the grade. And stick to this structure. I will change this one. This one correct, but this one I made a mistake. I miscopied it. But selecting the training we want. This one you don't need to, and this one you don't need to because we don't have those. Okay? Present your solution. Our solution really says the random forest is a better algorithm. Okay? Good? Questions?
no,
Yeah, almost. I have a question, bro.
What we're
Wait for
going to
people
do
to
next
leave.
week, but before that, what we're going to do next week, guys?
Go over it and the
Go
test.
over part of it, and then second, please go over the questions. You know, you have the questions here on every part we did in the course. Go over, take a test, and go over those questions. If there is any questions, you don't know the answer, or you do not understand the answer, please do it this week. Utilize me. I will go over questions you would like me to kind of highlight the answer or explain the answer in more detail. So please do it this week, and that's what we'll do next week, and let's conclude the course. Thank you, guys. And
Thanks,
last
Donald.
favor,